Okay, last example of the last practice of the static analysis is the problem statement as following. So there is an assembly with two bar, four components made out of a structural steel with the Young modulus of E200 GPA and Poisson ratio of 0.3, density of 7850, and it's shown in the figure. The bar identical in size, each bar 2 centimeter diameter, 6 centimeter, and some information about the thickness and other dimension. And the distance between these two end block is given as 8 centimeter. And it says, let's suppose that the two blocks are fixed from the bottom face, and then these two bar are going to pulled by a pressure load of 100 Newton per centimeter square in opposite direction. So it would be from here and here. It's a pressure load, and we wanted to compute the stress in the assembly using the finite element analysis. Okay. So if you open in a class shared material off of a file that I call it in the folder of the uh, this two bar and block, uh, I have defined this assembly. The, the block is defined, so two block here and then two bar here and there. There are some mates that you can go over the mates that has been defined here, and you have an assembly that is ready for the analysis. This underdefined is essentially for the rotation of this bar, which is not going to impact the result of the study. Okay, now with this part, with this defined, we go to the simulation and create a static analysis. It's going to be here. Now we have a little more to define for this assembly. First, you will see that because it's a multiple parts, they are all defined here, and then we can go and select all the material. So if you right click on it, you can define material each at a time, or if you right click on the parts, you can apply material to all. So that was going to save you some time in order to define it one at a time. So if I go to aluminum to 836 material to see what is the values were. Okay, now if you compare this value with the one that is given, you will see that when I select A36 for the structural steel, let's compare it with this one. You see that number one is the values are in English PSI, but the problem is given in SI unit. So you're going to change the unit from here to SI. And you will see that the elastis modulus matches. It's 200 GPA. Actually, Pascal is equal to 1 Newton per meter square. So that matches. Poisson ratio is a little off. Density matches with this one, and the yield strength is the calculation of this should be accurately should be here. So it would be 225 the rest of number here. So I think we have to just define a Poisson ratio, which is not going to impact on the yield or any other value. And then that would be a portion that sometimes we need to define a new material. So we cannot change this value because these are right from SolidWorks database. But what we can do is we can right click on it, go to copy, and then we can define some custom materials here that may have been defined. So if I select here and then create a new library, and it would be probably I can create a new folder even here. Let me see if I can create a new folder in this here. or new category. Okay, now say my materials, and then I can paste. Then the material that I have selected would arrive here. And here I'm going to change it. For example, I would call it structural steel. And then I can define this one based on the value that I would like to change. Going to select here based on 0.3. Going to save here. So the material and everything is defined, and then the rest of that is pretty much whatever it was, and then I can apply. So, and then when I close it, all of them would be a structural steel. So now the material has been defined as problem expected, and you'll see that we select the options for apply material to all, so all of the parts would share the same material properties. Now the connection is something that we have to define it. And what is the connection for? SolidWorks would like to know that if one part may penetrate into another part, meaning that is that possible that if we apply some force, this which is nice in this hole is going to penetrate into another material? And that is something that you as a engineer should define for it. Currently, you see under connection, and then it said component interaction, and there is a global interaction. If you go to definition, you will see that you can free or contact or bonded. Bonded means these materials are welded together, and free means they can freely move based on, you know, amount of the force that has been applied. So I would select bonded, meaning that this part may not penetrate into other parts. So that is the part that you can define. So connection is something that we have defined, and the default is what expected. We're going to fixture, and for fixed geometry, the problem said the bottom of these blocks are the fixed faces of the setup. Then we hit OK. And then we have to apply for another step, apply the external forces. And what we had here, the problem said, this is 100 Newton per square centimeter square, and it's a pressure load, and it's opposite direction. So I'm going to select a pressure load. And then I have to define what components this pressure applies, and it would be, I would say, this part and this part. Now, by default, SolidWorks wanted this to be based on, you know, perpendicular to that face, but this is not what a problem said. So we cannot select the normal to selected face. We are going to use a reference geometry to doing that, and I can select this edge as a like a horizontal direction of that. Then if I reverse direction, so the problem is it's better that we select one face at a time. So I will delete this one of them. It's only select this part, and then I'm gonna reverse it, reverse direction here, and the value that it says it was 200, no, 100 Newton per it should be centimeter square. So we have to define some calculation. So if it is a 100 per meter, it should be divided by, so it would be divided by 100 to power of 4. So essentially that would be 100 divided by power of 4, which is 0. So yeah, so 100 Newton per centimeter square would be equivalent to 0.01 Newton per meter square. And hit OK. Then we have to apply the same load on the pressure load on another part, which we select this part. It's getting using the different geometry, and that would be this one. No need to change the direction, so that would be 0, 1, and hit OK. So you will see that the forces are defined as problem expected. Now we are going to create a mesh. We can go by the default values of that mesh, and then we are going to hit OK. So you see that there are 4 parts that SolidWorks is trying to mesh it for the problem. It's expected, and all we have to do is to run the simulation. And this would be the exaggerate deform, which is expected. We'll see that this faces is up. Now this has been bended. The blocks also bended, which is again what we expected. Now the question is there any point in this assembly that is going to exceed the yield strength and eventually would be failure? The answer is no. And actually the stresses is fairly small for the values that is given. Let me review one more time to make sure that we did not lose anything. No, that is accurate. So it is correct, and it means that it's not gonna fail. If we are going to the displacement, you are seeing that this is the maximum displacement that is appear here. And if I'm looking at the stress, if I'm going to the animate, you will see that how this part is going to animate it. Okay, exit out of this animation. There are other cool features that is nice to for example see that. So first of all, if you don't want it to show these arrows, you can right click on it and hide it. It just remove the those you know, arrows from that. Same for the fixture. I can hide it to not showing here. And now one of the things is you'll see the exterior surfaces of the model for the you know, for these stresses, for this result. But we can, if you are interested into, let's say, create a section and see, let's say, what happens in the center of this rod for all of this pressure, you can right click on it, same place that you did iso clipping, but now you are going to go to section clipping, and it's going to give you what is the direction of the section that you want to see. It's selected front plane, but if I wanted to do the center, I would like top plane. So I can select top plane for that. Here is selected. Okay, select front plane and then hit top plane. There you go. And now that give you an arrow that you can actually pull it up, and you see at every point is going to, you see, and then this is almost the half of the bar. And if I hit OK to stay there, I can see what is the location of that, you know, how the stresses has been formed here. Or if I wanted to keep here and go to the displacement, it would be pretty much the same. I have to define the same, but that it stays here. So, and that would be essentially the one that you can create a section out of it. Now, if I'm going to go to so if you wanted to remove that, go to section clipping one more time. That, you know, the section clipping will be shown here, and then here you can turn it off. So, and then hit OK. and it's going to bring you back to the area that you were. Now, if you wanted to try how the other value, let's say instead of this pressure that we defined, let's say it was given as 100 Newton per meter square instead of centimeter square. So if I change it to 100 and again change back this one to 100, and you understand that it's the arrow is off but the values is still applicable, meaning that let's put 100. I can show them again for sake of showing them on the model, and then the result would be changed. That's why an exclamation mark is appear here, and then we do have like different values for that, but still it shows that we are in the safe region for this analysis. So okay, so and that would be the end of this simulation. If somehow when the yield and the stresses are again the yield strings, SolidWorks show an arrow here to just showing you that anything beyond that is not the one, and similar to what we experienced in the beam that was showing there. But you can save it, and then that would be the analysis. Okay, have a good day, and hopefully you have learned the basic simulation of the SolidWorks and using the static simulation. We are going to discover other studies mode in this simulation, and we'll learn more about its capability up to that point. Have a good day.